Hi everyone, today I'll be talking about how to leverage language models to generate natural language corrections for teaching physical control tasks, such as playing a sport or driving a car. If you've ever tried to learn a physical control task such as playing volleyball, you might remember it took a lot of time to start to improve. And there might have been certain skills, such as an overhand serve, that no matter how many times you practice on your own, you can never quite just get it right. What might have finally helped was having access to a coach who gave verbal feedback, such as hit the ball at a lower angle, or metaphors such as bend your knees like a spring. And in fact, prior works have shown that this kind of verbal feedback is actually important in increasing response rate and accuracy for volleyball. However, verbal feedback isn't always available. Sometimes we might be just doing self-practice without an instructor, or are learning complex control tasks such as operating a surgical robot, where there are few skilled teachers who could even provide this kind of verbal feedback. So in our work, we ask, can we automatically generate natural language corrections for physical control tasks? Concretely, we want to take student behavior for a control task and provide a corrective utterance, such as hit at a lower angle. In order to know that the student should be hitting at a lower angle, we need to incorporate some reference expert behavior. Furthermore, in order to generate text such as hit at lower angle, we need to consider a generative model, such as modern large language models. However, the important part is language models currently take in text as input, while student and expert behavior and control tasks are often of the form of trajectories, or sequence of state and actions. So we propose in our paper, CORGI, a model for generating corrective feedback that handles these trajectory sequences as input. Concretely, we represent student and expert trajectories as a sequence of state and action tuples. And then we learn a feed-forward neural network M that learns how to represent these trajectories as a sequence of vectors that have the same dimension as the vocabulary of a frozen language model. So then these vector sequences are used to construct a prompt that is sent as input to a frozen language model, and then the language model generates text, such as the correction hit at a lower angle. To train CORGI, we consider 3 different kinds of physical control tasks covering standard motion primitives: drawing, which is 2D states, steering, which consists of steering, 2D steering actions, and 6D states such as velocity and acceleration, and human body movement, where we consider videos and use video X-clip representations from the Babel dataset. So we train CORGI over these 3 different control types. And to collect data for training CORGI, we crowdsource language corrections using an annotation interface we built that shows pairwise expert-student trajectories and asks annotators to provide corrective feedback. And we collect 2,000 such annotations. So the first set of results in our paper are quantitative results, such as Perplexity. And we consider both in-domain splits and out-of-domain splits, which in drawing are different alphabets that were either seen during training or not. And we compare CORGI with permutations, where we randomly shuffle the correction and the student when evaluating Perplexity. And if CORGI is successfully sensitive to these aspects of the sequence, then it should have a lower Perplexity, which we observe. Furthermore, we ablate data augmentation and pre-training of the underlying language model and see that CORGI performs worse with these ablations. However, these automated metrics are limited because they assign high perplexity to examples such as metaphors in domain-specific language that might actually be pretty useful for teaching. So next, we consider a user study on human preferences, where we measure the rate humans prefer samples over to distractors. We consider a nearest neighbor baselines, where we use the feed-forward neural network to find the nearest neighbor in the training set and randomly sample reference annotations, and we find that CORGI outperforms this baseline for all 3 tasks. Furthermore, we also interestingly see that for the steering task, CORGI is better than ground truth annotations, which might be because CORGI generates more fluent text than references that pick up annotator noise. Finally, we conduct a user study where we actually use feedback from CORGI to conduct a learning experiment where users use the feedback to improve over time. And we find when measuring the error between student and expert trajectories that participants provided feedback from CORGI improved over time, while those in the control group decreased in performance. So our key takeaway here is that we've shown that we can leverage any arbitrary language model to generate personalized feedback for complex physical control tasks. And future work would consider long-term skill retention versus just the short-term learning experiment, and also how to handle multiple expert behavior, which is a more realistic setting. Thank you.